Okay, any thoughts on this problem? First of all, I want to make sure everyone understands that you need to return the cheapest flight from source to destination that has at most k stops, right? So if k is equal to 0, that means that you're looking for direct flights, right? If k is equal to 1, you're looking for flights with at most 1 stop, at most, right? You can still return a direct flight if that's cheaper, but you're allowed to make at most 1 stop.
So the first thing that comes to mind is using a heap. Is probably Dijkstra's algorithm, because you want to sort it by the cheapest flights. And then obviously, like if you go down a path that goes over your or
number of stops,
not go over, yeah, if you go over the number of stops, then I guess you just have to like return if you didn't hit your destination, and then you just keep on popping off the heap until the first destination that or the first node that reaches the destination.
Okay. So first of all, when you're during the interview, when you're describing do not mention the data structure, okay, before you talk about, you should talk about the algorithm before you talk about the data structure, because data structure is about implementation, right? Now, if you first, so you mentioned Dijkstra's algorithm, so you can mention Dijkstra's algorithm without mentioning a heap, right? Everyone knows that you can use a heap to implement Dijkstra's algorithm, but that's implementation detail, right? So you first need to make sure that the algorithm is correct, or so when you're doing Dijkstra's algorithm, the typical Dijkstra's algorithm just finds the cheapest, I think, in this case, the cheapest flight from source to destination, right? So how do you ensure that the cheapest flight you find has at most k stops?
So like if you do depth first search or breadth first search, each iteration is going to count as 1 stop.
Yeah. So how do you make sure that the result you return, of course, when you're doing Dijkstra's, of course, the result will be the cheapest, right? But how do you make sure that the cheapest flight has less than or equal to k stops?
Well,
so you need to remember the number of stops in the code, right?
Yes. This distance array, it normally remembers only one distance, which is the shortest in absolute. But if we might have to remember 2 things in that shortest distance array. So there might be shortest distance with one with not just 2. It might be like many shortest distances, remembering according to the number of legs that it has crossed already. So
okay. So you're saying in the easy Dijkstra's, we just we have a for every node we have the shortest distance to it.
Yes.
Right. But you're saying in this case, you actually want to, for every node, you want to remember the shortest distance for every number of stops.
Up to k.
Up to k.
If it has more than k, then we can put a
there's no point of continuing, right? So, but you're saying I need to know the cheapest flight to node 2 if I have 1 stop, 0 stop, 2 stops, 3 stop, like for every stop up to k. Like you want to sort that kind of information.
Array or dictionary up to of size k.
Okay. Daniel, do you agree with this? Or is this the solution you have in mind?
Wait, sorry, could you repeat that solution?
So I'm thinking that in the shortest distance array, instead of being an array of numbers, it is an array of dictionaries. And each of those dictionaries has the values from 1 to k, from either or 0 to k minus 1. There's so many legs. This is the shortest distance. So at any given point in time, we have so many, like if we also remembering how many legs we have crossed to get to this shortest distance. So if we get another shortest distance for a different number of legs, that does not supersede the one for a different number of legs. So when we are comparing, our normal algorithm was that we just compare it with the number, and if we get a shorter distance from a different route, we used to supersede it. Now we will remember both, that by 1 leg we got this distance, but by two legs we got this distance. So every time we get a new one, we know how many legs there are, because there is one more than whatever it was for parent. And now in that we update for accordingly.
Okay. So I want to illustrate the intuition, right? Why we want to keep the shortest distance to a node for every number of stops, right? So let's say that you have 3 ways to reach a given node n, some node n from source. Okay. So the first way is cost is 1,000, stops is equal to 2. The other one is cost is equal to 2,000, stops is equal to 1. The other one is cost is equal to 1,500 and stops is equal to 1. Now, among the 3, we what kind of information is needed? Like, do we want to remember? Do we care about the third way? Or do we care about the second way? If we have the third way, we do not want to remember the second way, right? Because if you're able to reach n using one stops, then why, with a cost of 1,500, why do you want to go there with 2,000, right? It doesn't make sense. Okay, now how about the first way on line 25? The first way we have to remember, because the first way is the cheapest way, right? It uses more stops, but it is the cheapest way. So we still want to remember, right? So it seems like for every number of stops, for every number of stops, we want to remember what is the cheapest way to reach this node in this number of stops, right? So basically, okay, how do we reach n if we allow one stop? How do we reach n if we allow 0 stop? How do we reach n if we allow 2 stops, etc.? But for a given number of stops, if we're like, okay, let's fix a number, let's say 3. So for 3, if I allow 3 stops, I should only remember one number, right? It does not make sense to remember more than one number for a given number of stops, right? So so just like in this case, if the number is 1, I just need to remember 1,500. Right? I do not need to remember 2,000. Right? So for a given number of stops, I just want to remember what is the cheapest, what is the lowest cost to reach n in that number of stops. Right, so that's why Sandesh proposed that we should use an array. So this distances, right? Remember, we usually use this distances array to remember the shortest distance from source to every node, right? But instead of an array of integers, now we actually want to do an array of dictionaries, right? So this dictionary will be like, okay, so if you allow 0 stops, then what is the cheapest? Maybe the cheapest is 3,000. And if you allow 1 stop, okay, the cheapest is 1,500. And if you allow 2 stops, okay, then the cheapest is 1,000. Right? This is for some node, and you will have another dictionary for another node, etc. So this is going to be a list of dictionaries.
So what would the second dictionary look like? So,
well, this is for the first node. Right. This is the first dictionary is for the first node. How do you what's the cost to reach the first node? Then the second dictionary would be what is the cost to reach the second node, etc.
So 3,000. Wait. So 3,000 is from 1,000 plus 2,000. But why are you adding?
No. So okay, let me complete it. Right. So 3 ways to reach n. Let's say n is 0 from source. Source is something other than 0. Right. So if you have 4 ways to reach 0 from source, then you would have this dictionary for 0, right?
Like starting from 0 or to 0 from source. So which one is your source? Oh, so your source is each one of these, like 1, 2.
No. Source is source. Source is something given by is in the input.
Yeah, but I'm wondering how you're getting these numbers. So 0, you're getting 3,000 at. But then index is for. Wait, is the 1, 2, 3, 4 are those nodes, or is that
1, 2, 3, 4. These are, let me call them A, B, C, D. So there's no there's no ordering, right? These are just different ways to reach 0 from the source.
Oh, I see. Yeah. Okay, so with 0 stops is 3,000, 1 stop is 1,500. Mm-hmm. Okay, yeah.
Yeah. So I'm saying this is the amount of information you need, right? Previously in the sort of Dijkstra's algorithm we have seen on Wednesday, the distances, what would the distances be? The distance would just be 1,000. For node 0, because we're just remembering the cheapest value, right? The cheapest value is 1,000, right? But in this problem, we need to also consider the number of stops we used, right? And so then the question is, okay, so do we just like what's the amount of information you need, right? Do you obviously need both the stops, the number of stops, and the cost, right? But do you need do you need to remember all of the possible pairs, right? But I'm arguing you don't need all of the possible pairs. For example, line 26 is not needed. Right? If you can reach it, if you have found the same number of stops but a cheaper cost, then you don't need to. Then that's the best one. Right? Does that make sense, Daniel?
Yeah. Yep.
Okay.
So that I was thinking of something like that, except I wasn't thinking of a dictionary. I was just thinking of a tuple. So like I was thinking like a heap of tuples of the stops and the cost, and that'll be ordered.
Wait. So hold on. So you're saying this is a heap instead of a dictionary. This is a heap. So it's like a list of heaps, or
no. Like the heap is the array, and then instead of the dictionary, you have tuples. So you.
I see. So 0, 3,000, 1, 150.
Yeah.
Okay. So the reason why it cannot be a tuple is you need to be able to quickly update that. right? So if I found a cheaper way to reach some node, you know, in 2 stops, I need to, so if somehow I discover that, okay, you can reach this 0 with a cost of 500 with stops equal to 2, then I need to be able to quickly change this 1000 to 500.
But why would you need to update it? If you just push it to the heap, it should already take priority over the original one. And then if that one hits the destination, you just return. So you never even finish the rest of the heap. So like if you push it, like let's say you have this 502, and if you push in 502, then that will go in before the other 1502 or 1002.
Yeah, but then wouldn't your heap be too large?
Oh, I see. So okay.
Because the heap actually contains a lot of unnecessary information.
Yeah. And the old one, there's no way to bring it out, right? So
yeah, but no. So I think so. Daniel's point is that you don't need the old ones to be removed, because you're not going to get to the old ones, right? So Daniel is saying that the heap can contain both to 500 and to 1000. That's okay, because to 500 is going to be processed earlier than to 1000.
Yeah, but
right. So
the space. Yeah,
but yeah. So your function you will not return the wrong answer. That is true, but the heap will grow very, very large.
Yeah. Mm-hmm. I see that. Yeah.
Yeah. Okay. Daniel, do you want to implement this one?
Okay. Yeah. I'm still. So for the dictionary one, 0, 1, 2. So like, could you?
So we're still using a heap. We're still using a heap.
Yeah, but for the dictionary, so like the way I was thinking about it for the tuple was like 2 and 5 would be just together, but then in the dictionary you're grouping 0, 1, 2 in one dictionary, and then 0, 1, 2 again in the next dictionary. Is that right?
Yeah. So okay. So in the 500, right? So if you say 500 is a tuple, but that still you need to associate that with a particular node, right? That is the cheapest way to reach 0, right? That's not the cheapest way to reach 1 or something, right? How do you? I think still you need to include that information in the tuple.
So I'm just wondering what the second dictionary looks like.
Well, the second dictionary is the cheapest way is to reach 1. Remember, you have n nodes.
Oh, okay. I see. But then we wouldn't need to. Well, so we only need So why are we keeping track of all of them? Like, don't we only like we're given the destination? So don't we only need to keep track of 1?
Yeah, but well, in order for us to get to some node, we can get to that node from many previous nodes, right? So we need to remember the cheapest way to reach the previous nodes.
Oh, I see. So this is like kind of our graph then, our adjacency list, or?
No. So the graph is the graph. Actually, you know what? Maybe it's easier if you try to implement using tuple. If you already have that in mind, then we can we can work from there.
Okay.
Yeah.
Okay. So basically, I want to create a heap with. So okay, let me just build my graph first.
Okay.
And then we have, I think it's from, to, and price. So this is directed, right? Is this directed or undirected?
This is directed.
So graph at from. Okay, so once we have our graph, so we have a heap. Basically, what we want to do is push in the source, and then for all of its neighbors, we push in, and basically we only push them in if k plus 1, or if the so basically we start our heap with source and the number of stops, which starts off at 0, and then for each node that we're going to push in, we're going to add 1 to it. And basically, if we add 1 to it and it's greater than k, then we don't even push it to the heap. Okay. But if it's less than k, then that means we're allowed to. And then from there, like we're basically going to keep on popping. We're going to pop the smallest cost first, and if it's equal, if the node is equal to the destination, then we just return the price. So we're going to start off at. So we're going to push in the price too. So we're going to start off at 0 price as well. So we'll heap. Then we're just going to pop. So it's going to be, we'll call this C. And then the middle one is going to be the price, and then the right one is going to be K. Basically, we can check if C is equal to destination. We just return price. And then I don't think we need to keep track of like a visited because it's I'm assuming this is acyclic. Actually, can I assume that?
You cannot assume that. But as we have seen before, you don't need a visited with this.
Oh, because I forgot why.
Like, what's the benefit of having a visited?
To prevent cycles, right? So,
but a node will be visited multiple times, right? That's why we need to update, because we do need to update our shortest distance.
Actually, also, I remember you explained this, but when I sat down to doing some problems, I realized that otherwise, what if in this, so there are nodes for which we've processed all the children. Now we do not want to go to those nodes, even if routes exist, right? So if there are cycles in the graph, then in this one they aren't. But if there are cycles in the graph, then we do want to avoid them, right?
Well, you won't avoid them no matter what, because you only push to the heap if you're going to shorten the distance, right? But if if for nodes that have already been processed, you're not going to shorten their distance.
You'll not shorten the distance, but you'll still traverse. You'll still continue the traversal, which will take your resources, no? So you will you'll come to that if where you're finding the max between what the shortest distance currently is and the last shortest distance plus last leg. So that you will choose what it was. So you won't touch anything. I agree. But the node will again get placed on the heap, right? And
which node? Which node will again get placed on?
You're placing double crossing.
Well, you're placing a neighbor on the heap only if the neighbor's neighbor's distance has been shortened, right?
So then you're saying that shortest distance array also doubles up as a visited.
Yeah, exactly.
Okay. Then I think should be accordingly. Makes sense.
So basically, I'm keeping in my heap, I'm popping the price, stops, and city. If the city is the destination, I'm going to return the price. And I basically check if stops is less than k. Then if stops is less than k, then I know I can like continue adding to the heap. But if
what if it's equal? What if it's equal to k?
Well, if it's equal to k, we don't want to, right? Because then
well, so if k is 0, that means you allow direct flights.
If k,
right? So it
right.
So
stop it. Yeah.
Okay. Sure. Yeah.
Right. So if k is 1, start at -1, then we can 1 stop.
I would just instead I would maybe on line 10 just say less than or equal to k.
Okay, but the thing is, I'm starting at 0, and then if I add 1, then the next time I can add another neighbor. Right. That would make it k. That would make it 2. Oh, this should be stops. Right. Like if stops is 0 and then k is 1, then I'm going to heap push another stop. So it's 0, and then it's going to check if 1 is less than or equal to 1, right? And then it is, and then it's going to heap push 2. Which
well, that's okay. You're allowed if you're allowed to make 1 stop. Right. That means
Right. Yeah, because I'm not counting the second one, right?
Exactly.
Yeah. So okay, yeah, that's a yeah. So this should be in order. Yeah. So if I do have stops left over, then I can check my neighbors and push them to the heap and add the price to my current price, and then the heap will order the stuff by price basically.
Okay. So I thought the heap you're storing tuples, right? I thought the first one is the price, the second one is the number of stops, but on line 12 you are p plus np is the cost, right? But
that's
then then the next one should be stops plus 1, then the last one should be nc.
Oh yeah, you're right. Yeah. So this is neighbor let's see. Oh, neighbor city. Yeah, city. And then so it will be ordered by price. And then if the stop, as long as it falls under the stop. So once we hit our destination, it should give us the right answer. And we're always assuming. Oh no, so if
you can if you cannot reach it, then return -1. So yeah, this is fine. I think it's going to complain. Yeah, see double equals, and also heap pop. Does Leetcode know heap pop? Do you need to import?
Yeah. No, you don't have to.
Okay.
Push expected to.
Yeah, on line 13, you need to give it the heap.
Okay.
Okay. I think it's going to time limit exceeded.
Yeah. Looks like. Yeah. So that's why we have to go through.
Yeah. So okay. So let's think about what why it's slow. So you're putting all possible. You're essentially not being selective in what you're adding to the heap. Right? You're adding everything to the heap as long as they don't exceed the number of stops allowed.
Yep.
Right? Okay. So so think about it in Wednesday's class when we were doing those extras algorithm problems, we usually have a step like we say, okay, if the new cost is smaller than the old cost, only then do we push to the heap. Right? But you don't have this step here. You don't have this thing here, right? So here on line 13, you're always, for every neighbor, as long as they don't exceed the number of stops, you're just going to add to the heap.
Right. So we can keep that the distances array.
Yeah.
That has like the cheapest price, and then for every basically we only want to push it in if it's less than the price in our distance array, and then we update it.
But how about the number of stops?
Number of stops.
So what if you? What if the current way is actually is no cheaper, is more expensive than the old way, but the current way uses fewer stops?
But then, well, like, so fewer stops. Like, we don't care about the number of stops as long as it's under K, right? So.
Well, yeah, but if in the end you want to reach N, but there's a easier, there are two ways to reach, like N's parent. One uses exactly K stops. The other one uses K minus 1 stops. You actually care about the one that uses K minus 1 stops, right? Because if you've already used K minus 1 stops to reach N's the destination's parent, then you need exactly K stops to reach N. Does that make sense?
So if we can reach N with K stops versus N with K minus 1 stops, you're saying N minus 1 is better?
No, I'm not. That's not what I'm saying. I'm saying I don't know which one. Like in the end, I only care about N, right? But let's say N is the destination. I only care about the number of the cheapest flight to the destination, right? But I don't know that, right? I don't know. And so you like what is so in order to figure that out, you need to know what is the cheapest flight to the destination's parent, right? Now, so how many stops to the destination's parent? What if you've already what if the cheapest way, okay, how about this? What if the cheapest way, okay, let's say K is 3. Okay, let's say K is 0. So you're only allowing direct flights. Okay, so somehow there is a very, okay, let's say K is 1. Yeah, let's say K is 1. Okay, so there are two ways to reach the destination's parent. One already uses 1 stop, okay, but it's very, very cheap. All right. The other way is a direct flight to destination's parent, but it's very, very expensive. Right. So which information is needed? And let's assume there's no direct flight from the source to the destination. The only way to go to destination is through that parent. Right. Now at this point, in this case, you actually the only way is to go to the more expensive direct flight. Right, because you're only allowed 1 stop. And the cheaper way to reach the destination's parent already uses 1 stop, right? So so you cannot go further from that parent to the destination.
Yep.
Right. So what I'm saying is, just because it is possible to reach a place cheaper does not mean that's the best way. Right. So of course I want to know what is the best way, what is the cheapest way to reach every node for
every stop,
for every number of stops.
Right.
That's why in the beginning I said it should be a list of dictionaries, not just a list of integers.
So I started implementing this list of dictionaries thing, but the problem is that when we are putting, they will still have only 1 heap, right? So in the heap,
still 1 heap.
Now in that heap, what comes first? See, in the conventional Dijkstra's algorithm, we traverse the nodes in from lowest to highest among the unvisible nodes.
Yeah.
Now the concept of lowest to highest, I am writing the comparator for that, and the problem is that I have 2 things in my hand. One is the stops, and the other is the prices.
Yeah,
Now-
so still you should prioritize the price.
and ignore the stops. So
No, if there's a tie, of course you would.
yeah,
You know,
if there's a tie, if there's
the
a
smaller
tie,
number of stops wins.
then smaller is better, as you explained.
Yeah.
But wouldn't I argue exactly the opposite way also? That I should prioritize, I should say stops, and then why would I not say that?
So the difference is if you prioritize on the number of stops, then when the moment you pop destination, the moment you're currently visiting destination, you cannot stop at that point because there may be a cheaper way to reach the destination with that uses more stops.
Makes sense.
Right. But if you're prioritizing on the total cost, then the moment you see the destination, you know that's the cheapest way.
Yeah.
I'm wondering if I could still implement this like with an array of stops, like and like just having the minimum for each stop.
Sure. Yeah, that's fine too.
So like if we keep it like this way and then stops array for each stop, right? So
Okay. So, but the thing is, how do you differentiate each node? So like, how do I know the the cheapest way to reach like node A in 3 stops? How is that represented? How can that be represented by this stops array?
so node A in 3 stops. Okay, yeah. I mean, you can't.
I think this can be done, but this needs you need a 2-dimensional array.
Okay, and the reason why we need okay, I think I see it. So we're keeping track of every single one, like every
node
at every stop.
Yes.
Okay, and then that'll help us save space basically. Basically if we're at stop 1, and we're hitting node B and we see that node B is already in our dictionary, then we know not to push it in because or if the cost is larger than the one in the dictionary.
Yeah. Then you don't need to push to the heap.
I see. Yeah, that makes sense.
Yeah.
Okay. Should I implement that?
Yeah.
All right. Close. Okay, so we have this array. Basically, we want to update for each k, right? So.
Okay, so this is an array
Of dictionaries.
of dictionaries, but you have k such dictionaries.
Yeah.
So in each dictionary, it is what will the key and the values be?
So the key and value will be the node as the key. Or actually, wait. Yeah, the node.
Yeah, I think if you're written like this, then yeah, the node will be the key, and then the cost will be the value.
Yeah.
Sure. Yeah, we can do that.
Yeah. So we're still gonna check if the stop's less than k, and if it is, then we're gonna compare it or see if it exists in our stop.
So I think that will come after line 13, right? Because this is different for each neighbor, for each city.
If S is already in, or so if S is not in, stops at S like -1 or yeah, so we're starting at 0. So I think
so S is the number of stops to C, right? But now you're talking about NC, so you actually need to increment S.
So plus, okay, yes. So
let's increment S outside of the for loop because you need to increment S in all cases for every neighbor.
The thing is, this is 0 index, right? So we're okay. So this should be k plus 1 then, right? For range of k plus 1 because we want to go up to k, right? Like if it's 1 stop and 1 stop.
Yeah.
And then we have to ignore index 0. Like nothing should go in index 0.
Yeah.
Okay. So yeah, that makes sense. So if S plus 1. So if it's not in our stops, then basically we want to add it in. That NC is going to be equal to NP basically. Otherwise, we're gonna do a compare. It's equal to the minimum.
Wait. So stops of online 13, stops of S+1. This is a dictionary.
Yeah.
Right, online 13. So stops of S+1 is a dictionary. So online 13, shouldn't you be doing if NC is not in?
Oh,
instead
yeah.
of S+. Yeah.
Right. Yeah, sorry, this is 2D. So yeah, NC is not in okay, yeah, so S+1 always exists. So
yeah, if NC is not in this dictionary, okay, then you're going to is it NP or it should be P plus NP, right?
Yeah, P plus.
Okay. Yeah, if it's already there, then you need to
set it equal to the minimum.
Set it, yeah, equal to the minimum. And then you need to be, then there need to be a condition, when do you push to the heap? So
right, so you only push it in if
well, if it's not there, if it's not there, or if it's smaller than the existing one.
So I'll get rid of the minimum. So
yeah.
So if it's
if P plus NP is less than that, or
it's greater.
Well, if it's equal, okay, let's think about it. If it's equal, then
you don't want to update, right?
The updating is fine because it doesn't change anything. But the question is, if it's equal, do you push to the heap?
Well, okay. If it's equal,
if it's equal, why do you want to? Then nothing happened, right? Because if it's equal, that means it's the same number of stops in the same cost. So there's no point of adding it to the heap.
Yeah, I don't think you should. Yeah, I don't think you should. Yeah. And this is equal to n plus.
And also, I think after line 15, you need to push after line 14, right? So line 14, if it's currently not existing, you still need to push to the heap.
Right.
Okay, yeah, this makes sense. So if S is equal to K, then maybe it should be range of K plus 2. Let's try that. On line 7.
Oh yeah.
Let's try K plus 2. Yeah.
I think, and yeah, this is
yeah.
Or I could just do Oh yeah. Thanks.
Yeah. Good. Okay. So during the interview, right, I expect you should be it's you get to you are able to get a working solution, right? Of course, it was not the most efficient one, but it was correct. So I will still give you like a pass, but not going to be like so it's going to be on the fence, right? Now, how do you? Of course, during the interview, you definitely the goal is to impress the interviewer, right? But we cannot do that in all cases, right? Maybe the problem is really difficult, or maybe the interviewer is not happy today or something. Like you may not be able to impress in every round, but still there's like a few small things you can do to make the odds in your work towards your favor. So you can provide more test cases, or you can propose ways to like. So first, the most important thing is you need to recognize why it's exceeding the time limit. Of course, in the interview, there's no one's going to ask you to run the code. So, but still, you need to understand where the inefficiency is. So in a real interview setting, it's actually more difficult because you cannot run all of the test cases, so you do not know if your solution is optimal or not. Right. So you need to, in this case, you need to understand that we're pushing every possible tuple into the heap, right? So that's actually not Dijkstra, because Dijkstra assumes that you're being selective, right? But you're not. So at least you should be able to recognize that this is probably where we can further improve. As to can you improve it, that's a different story, right? But I expect a good candidate to understand that this is probably where the inefficiency is.
Right. And is it okay, like if I go, like I'll finish the proof first, and then the interviewer tells me like, can you improve it? And then I get the solution.
Yeah, that's totally fine. But I think it would be better if, so it's totally fine if the first draft is not the optimal. I think in some cases, even if you know the optimal solution, you can still implement less than optimal solution, as long as you know that the less than optimal solution will lead you to the optimal solution. Like if you know that this problem can be solved using like a BFS, but somehow you decide to, you know, like do a brute force or something, then that would be stupid, right? Because you would have to erase everything you've written and rewrite everything, right? But in this case, the optimization really builds up on the brute force, not the brute force, like on your you know, your first approach, right? So this is definitely a good starting point. But the thing is, you should be the one who realizes that this is not optimal.
Right.
Right. So if you can, so do not, like after you finish this, you can say, yeah, I think this is working, but may not be the most optimal. Right now, let's see how we can further optimize this. Right. And now you cannot, so then the only way to understand how we can optimize on an existing code is to understand where the inefficiencies are, which is where are we doing duplicate work. Right. So in this case, we're doing duplicate work because the heap is taking in a lot of unnecessary tuples, right? And the heap pop operation is log n, where n is the size of the heap. So if your heap grows very, very fast, then your heap pop is going to be pretty slow, right? This is different if we were not popping. Instead, if we were just looking at the smallest value, like if we're just peeking the smallest value, then this will be okay, because you know, peeking is O of 1, no matter how large your heap is. It's O of 1 always. But if you're popping it, then that's log n.